All right, ladies and gents, now we are at the final section of this Chemistry Regents exam, Part C, where we have the last set of questions from 66 all the way to the last question, 85. All right, and we start with number 66 through 68. All right, number 66 asks us to identify the element in the data table above that is classified as a metalloid. So when we think metalloid, you have to think as an element that is in between metals and nonmetals. So we had to look at the periodic table and see which of these lie on that bolded staircase. Okay, and here this bolded staircase is what I'm referring to. Those that touch it are classified as metalloids. Now, looking at each of our elements here, Na, Mg are not there. Phosphorus is not touching it, sulfur isn't, chlorine isn't, and neither is argon. So it's between aluminum and silicon. And there's only actually one right answer, and it's actually silicon. And that's because aluminum, though while it does touch the staircase, it has properties that are more like a metal than a non-metal. So it is that sort of gray spectrum, whereas silicon is more in between, like an actual metalloid, whereas aluminum leans more heavily on the metal side than the non-metal side. It has very strong metallic properties compared to other metalloids. So it is kind of like a gray broad spectrum, and it's not some shady gray areas there, but to keep in mind that aluminum is definitely one to remember is most likely a metal, and silicon is strictly, absolutely a metalloid. And that's our answer for number 66. All right, 67. State the phase of chlorine at 281 Kelvin and 101.3 kilopascals. So chlorine is right here. These guys at STP, for the most part, are gases at STP. So chlorine is a halide, halogen. And kind of just know that these guys are gases at STP, especially group 18 over here. All right, number 68, state evidence from the technician's data which indicates that sodium is more active than aluminum. So we're looking at the data table. Sodium is right here, Na. It reacts vigorously with cold water, but basically no observable reaction with aluminum. So that's a piece of evidence. It reacts vigorously with water. Okay, number 69 to 71. Here we have an equation with ammonia, and it's saying that it's used as a substitute for fossil fuels in some internal combustion engines. The reaction between ammonia and oxygen in an engine is represented by the unbalanced equation below. So we gotta fill in their coefficients and balance this equation. So when balancing equations, we gotta make sure we follow conservation of mass. So that means the number of atoms on this side equals the number of atoms over here, especially for each element. So it involves a lot of back and forth backtracking things. Okay, so let's start with oxygen. Actually, let's start with nitrogen, just because. Nitrogen. We have one nitrogen over here, but on this other side we have two nitrogens. So to balance that out, 1 to 2, let's just put a 2 right here. Okay, got two nitrogens there. Now we're even on terms of nitrogen. Now let's look at hydrogens as a result. What happened to the hydrogens after we put that 2? So originally we only had 3, but now that we put a 2 here, we doubled the amount here. And we get 6 hydrogens on this side, which means on this other side we should also have 6 hydrogens. In order to balance that out, we're going to put a 3 right here to make it 6 hydrogens as well. Because originally there are 2. If you put a 3 there, you make it 6. And now the last thing we got to balance out are the oxygens. Now this is where things can get a little tricky. So here we have 3 oxygens. Over here we have 2. How do we make it 3 oxygens on the left side? Well, I'm going to put this temporary 1.5 here. Okay, so do we see that at the moment? So 1.5 times 2 gives us 3 oxygens. So right now it's balanced, but it's not whole number coefficients. So to make these whole number coefficients, what I'm going to do is double the amount here, double each of these guys. So what I'm going to do, I'm just going to erase for a moment. And this is what we get. Now let's double check. We got 4 nitrogens, 4 nitrogens, 12 hydrogens, 12 hydrogens, 6 oxygens, 6 oxygens, and we're good. That is your answer for number 69. Number 70 now is asking for a numerical setup for calculating the mass in grams of a 4.2 mole sample of O2. And we have to use this as our gram formula mass of O2. So we got to figure out the mass given moles and gram formula mass. So this is an equation on table T for this, where moles equals mass over molar mass or gram formula mass. So let's plug in what we have. 4.2 equals our mass over the molar mass of 32. Okay, and that is our setup. That's an acceptable setup. Because what you need to do is just multiply and you get the mass. All right, number 71, I'm going to do this over here. Determine the new pressure of a 6.4 liter sample of oxygen gas at 300 Kelvin and 100 kilopascals after the gas is compressed to 2.4 liters at 900 Kelvin. All right, so this is going to require the combined gas law. This is also table T. And look, nothing is being held constant, so we're going to use every single one of these values. So on the left side, we're going to start with our initial values. Where did we start with? Okay. We have 100 kilopascals as our pressure, volume of 6.4 liters, over a temperature of 300 Kelvin. Our new pressure is what we're looking for. Volume of 2.4 liters and a new temperature of 900 Kelvin. All right, and so all you have to do is do the algebra and figure it out, and you should get 800 kilopascals as your pressure. And that's your answer for number 71. All right, number 72 to 76 is talking about organic chemistry. And here we're going to, for number 72, write the empirical formula for ethene. Ethene is given as this. We need to reduce it to simplest ratios, and that's what it means to be empirical. So reducing 2 and 4 to the smallest whole number ratios, it's going to be CH2. Now number 73, explain in terms of bonding why the hydrocarbon ethene is classified as unsaturated. Because it contains a double bond. And that's why. Any double bonds or triple bonds, so alkenes and alkynes, are considered unsaturated because of the presence of those double bonds and triple bonds. All right, number 74, determine the gram formula mass of ethene. So we need to look at the reference table to figure out the molar mass of it. So we need to look at each of the atomic masses for both elements, carbon and hydrogen. Carbon has 12. Hydrogen has 1. And we multiply by the number of each of them. So times 2 times 4. And we add both of these up to get 28 grams per mole of C2H4. Number 75, particle arrangement, why the entropy of the water decreases when the water freezes. All right, so we need to talk about how the particles are arranged and entropy. So entropy is all about disorder. Why does it decrease when water freezes? All right. So what we need to say is that when water freezes, the particles become more structured and less random. That's an example answer that I would accept. Because you need to talk about how the particles are being arranged. They're less random, they're more structured, especially when you freeze to the solid phase, where it's the most structured phase of the three that we learned. And that's why entropy decreases, because entropy is all about randomness and disorder. It's less, there's more order, basically. Number 76, determine the quantity of heat released when 2 grams of H2O freezes at 0 degrees Celsius. So quantity of heat when it freezes. So we're going to look at a phase change heat equation. And that's on table T. And that's Q equals MHF, heat of fusion you use when it's freezing or melting. So the mass is given to us as 2 grams. HF, you got to look up on the reference table. It's on the front page, table B. And HF is equal to 334 joules per gram for water. And since we're talking about water, it's the appropriate number to use. So 2 times 334 will give us our answer, and that is 668 joules. And that's our answer for 76. All right, 77 to 80. Here we have a voltaic cell, because here we have 2 half cells, a salt bridge, and a voltmeter, which are the known components of a voltaic cell. So here we are looking for the form of energy that is converted to electrical energy. So for voltaic cells, you go from chemical to electrical, because it takes the energy from a chemical reaction to produce electrical energy. All right, whereas electrolytic cells go the opposite way. All right, 78. State in terms of the electrodes the direction of electron flow in the external circuit when the cell operates. So first of all, which one's the anode and which one's the cathode? We can look at our redox reaction over here and identify which one's oxidizing and which one's reducing. And the phrases I like to use is Leoger, and anox, and red cat. So losing electrons you oxidize, gain electrons you reduce. So let's look at copper. Copper is going from 2 plus to 0 in terms of oxidation states. So it's gaining electrons, whereas zinc here goes from 0 to 2 plus. It lost electrons. So copper gains, zinc loses. So zinc is being oxidized, copper is being reduced. And looking at the other two phrases, when you oxidize, you're the anode. So the anode oxidizes, reduction happens in the cathode. So let's do this. Anode. So this is here. Copper electrode is the cathode, and the zinc electrode is the anode. Because the anode loses electrons and the cathode gains electrons, the flow of electrons goes this way, from anode to cathode. If you struggle to think of that logically or remember that, here's a phrase for you guys. Fat cat. Tells you the electron flow. From anode to cathode. From anode to cathode. Okay. Now 79, we have to write a balanced equation for the half reaction that occurs in this half cell. So in this particular half cell, we should know that reduction occurs. So we're gaining electrons. We start with Cu2+. It gains electrons to become Cu. And that's how we show it. If you're losing electrons, it would be flipped the other way around. Number 80, state what happens to the mass of the Cu electrode and the mass of the Zn electrode in the operating cell. So if you gain electrons, you gain mass. If you lose electrons, you lose mass. So this one gains, this one loses. And we still have conservation of matter, conservation of mass. One gains, the other loses. And we finally arrive at the very last page of this Regents, numbers 81 to 85. At the home stretch, guys. All right, now we have a solution here made by dissolving 70 grams of KNO3 in 100 grams of water at 50 degrees Celsius and standard pressure. We have to show the numerical setup by calculating the percent of mass of KNO3 in the solution. All right, so percent composition is on table T. So we get the mass of part over mass of whole. And we times it by 100. And that's our equation, which will help with our setup. The mass of the part we're concerned about is the KNO3, and that's 70 grams. Now the mass of the whole we have to be careful with. It's not 100 grams, it's the solution. So it's a 70 grams of KNO3 and 100 grams of water. Together, that's 170 grams of the solution. And that's all you need to show for your setup for number 81. You don't need to calculate the answer. Number 82, determine the number of additional grams of KNO3 that must dissolve to make this solution saturated. So we're going to use a reference table. All right, so our temperature here is 50 degrees Celsius. So we need to go to 50 degrees Celsius and go all the way up to the KNO3 line right here, because that's our line of saturation. And look how it changes with the temperature. So when we reach this point, we reach saturation. And this amount right here is between 80 and 90. It's not quite in the middle yet. It's a little below it, so I would say that's about 84. You're allowed to be within a certain range, okay? There are some acceptable answer ranges. So we have 70 grams to start with. You need 84 total. So the difference between that is your answer. Because if you're over here and you need to be up here, that requires about 14 grams, okay? Let me get rid of this. So that's your answer. About 14 grams. All right, last group of questions. Number 83, explain in terms of particles why Hc2, H3O2 can conduct an electric current. Okay. Now if you look right here, this is an acid. And acids are mostly given off by that H+. Look at that H, it's right in the front of it. It's going to give off that H+ and dissolve into the ions when you put it in water. Hence why it's an aqueous solution. So having ions, mobile ions, is the reason for an electric current. And that's the particle part that you need to mention in your answer. It has mobile ions. Number 84, state the color of bromthiol blue indicator in a sample of the commercial vinegar. So we're going to need to use the reference table for this. All right, bromthiol blue is right over here. And the color change is from yellow to blue. It goes from yellow to blue, somewhere within this range. If you're below 6.0, then you're definitely still yellow. If you're above 7.6, then you're definitely still blue. Okay? But somewhere in this middle range is a possible color change. And looking at our pH value, we have a pH value of 2.4, and it's definitely below 6.0, so it's definitely yellow. Number 85. State the pH value of a sample that has 10 times fewer hydronium ions than an equal volume of vinegar sample with a pH value of 2.4. So hydronium ions are definitely related to acids. All right, so hydronium is H3O plus, and that's related to acids. So if you have less of those, we're less acidic. So I'm not boxing the final answer yet. This is not our answer. So we're less acidic. And every factor of 10 gives you 1 pH unit. So if you have 100, that's 2 pH units. It has to be a factor of 10. So if we're less acidic and we're different by 1 pH unit, let's think. Are we going up or down? So the pH scale goes from 0 to 14. 0 is most acidic, and 14 is most basic. So if we're less acidic, we're going to go towards 14. We're going to go higher on the pH scale. So our final answer, we have to add 1 to our original pH, and that's 3.4. And finally, that is the end of this chemistry Regents. Hope this is helpful for you guys. Make sure you check out the other parts in case you didn't. Best of luck.